So, as you can see, first speaker this afternoon is Viveka Erlandsson, and she's going to tell us about counting geodesics or even computation. Thank you.
Thank you to organizers for inviting me. It's great to be here. It's my first time in Madrid. Yeah, so I'm going to talk about this joint work with Juan Soto, and it's going to be about counting certain geodesics. So let me just start by the setup. So I'm just going to consider closed hyperbolic surfaces. They're going to be oriented, even though it's not essentially most of what I say, but connected. And the genus, just to be annoying, I'm going to call it A. G is going to come up later. So that's everything's going to take place on a closed hyperbolic surface. So we're going to count closed geodesics. So gamma is going to be an oriented closed geodesic. So the colors are not really coming out, but so all closed geodesics, not necessarily simple, they can self-intersect as much as they want. I'm going to think of them just as closed geodesics, but also identify it with free homotopy classes of loops, so immersed loops, or also as conjugacy classes in pi 1 of the surface. So I will use all three things interchangeable. So C is going to denote the set of all such closed geodesics, and C of L is going to be those of length across L. So Peter already told us a bit about this. So it's a classical problem to count such geodesics. So what we mean by counting is, so if I fix a bound of a length, there's always finitely many closed geodesics with most that length. But it goes to infinity, as L goes to infinity. So counting geodesics really means like at what rate does this go to infinity with L? That's what it means. So we already heard about Hooper's result, so from 59, that on any closed hyperbolic surface, this is asymptotic to e to L over L, with asymptotic meaning that the ratio in the limit is 1, so there's no constant missing as L goes to infinity. And there's many generalizations of this result, so which I'm not going to talk about today, but one can generalize it by changing the surface or changing the manifold. So first off, there's the same result is true for finite areas. You could have cusps. So I think the Hayhall was who first proved that, but then Margulis generalized this to variable negative curvature and higher dimensions and so on. And there's also more general notions of nozzle flows. The entropy will show up here instead of L, you will get HL, where H is the entropy. But what we're going to talk about today is a different kind of generalizations, where instead of counting all closed geodesics, we count some subset of closed geodesics. So, for example, one can count closed geodesics that are trivial in homology. So that's what we're going to talk about, and more specifically among those, we're going to talk about those that are fixed commutator length. So I will explain what I mean by this in a second. But if one wants to count all closed geodesics of length at most L that are trivial in homology, this has been done independently by last time I gave this talk, I realized that I completely mispronounced the name, and now I don't remember the right way. Katsura? Is that it? Okay. Katsura, Sunanda and Phillips-Sarnak proved this in the 80s. So that the number of, so the subset of those that are trivial homology grow like e to the L over L to the k plus 1, and a constant, the topological constant, so k again is the genus of the surface.
So Katsura, Sunanda.
Yeah. Sunanda, yeah, misspelled it, sorry. There should be a U and not an A. I don't normally make slides. Okay, sorry, yeah, misspelled. Okay, so what do I mean by a commutator length? Well, your homological trivial, if and only, can be written as a product of commutators. So the commutator length of the curve is the smallest number of such needed. And I guess if you're not homological trivial, it will be infinite commutator. So what we're going to count now is instead, so among those that closed curves are hyperbolic length at most L, we're going to count those of a fixed commutator. So equivalently, we can think of this as, so if you're homologically trivial, there's a surface with one boundary component and a continuous map such that the boundary component it gets mapped to a curve gamma. So the colors are really not showing here, but this might be some very complicated curve here. It's just a continuous map of my one boundary surface where the boundary gets mapped to my curve gamma. Okay. And then the commutator length is then equivalent to saying the smallest genus of such a surface. And that's where I'm going to use G, that's why I didn't use G. So in this example, right, if I take the standard generating set of this one whole torus, so the boundary has been written as one commutator in general. If it's genus G with one boundary component, the boundary can be written as a word that consists of G commutators. And then, so in this example, this red curve here, it has commutator length 1, which is the genus of this. And we'll refer to this as a genus G filling our curve. Okay. So what I'm going to talk about today then is so B, so G of L is going to be the subset of the closed geodesics, so hyperbolic length L, that has commutator length exactly G. And we want to see how does this grow? Well, the number of such things grow as L grows. So G stays fixed, but L grows. Okay. So we prove this, that for each G, we get this asymptotic growth, where C is a constant. You might not be able to see what that says, but the only thing that's important is to say what C is, and it's just a topological constant. Depends on the genus, this G, and on the topology of sigma. So it's some constant. Okay. So yeah, so one can also get, maybe if I have time, I remember I can tell you how it's not obvious at all that this is correlated to this, but basically the methods we use to prove this, one can also answer the following question, that if I look at those, so not all of this is going to bound as, we can think about a homological trivial curve as bounding a surface, a subsurface in there, but really it's a continuous image of a surface. So if one want to think about it like that, maybe one thinks more natural to talk about immersed subsurfaces, and how many curves of length of nose L bound, say, one whole torus, an immersed one whole torus, and there's this fraction of all of them. Right, so how do we prove this? So it boils down to counting certain graphs. So again, it's going to be somewhat related to what Peter told us about. So I call them fat graphs, but it's the same as the ribbon graphs. So, and I think of this, so it really is, just like Peter said, it's if I take a thickening or neighborhood of the graph, I get an oriented surface with boundary. I think of this as a graph together with a cyclic ordering at each vertex of the half edges there. So, and I'm going to say that a fat graph has genus G if the neighborhood of it, so the thickening of it, is a genus G surface with just one boundary component. If there's more boundary component, it's not a genus G surface greater G. But so as an example, my pictures are not at all as nice as Peter's, but here is, if we look at this data graph, so it has two vertices, and I orient them like this, then one way to get this fat graph structure on it is if I draw supposed to be a hexagon around each vertex, and I order them according to the ordering, and then I glue, so I want to glue the blue edges together, but with reverse orientation. So if I do that, I get something like that, and just by you can check that so the red bound, there's only exactly one boundary component, and using the Euler characteristic, you see that it has to be genus 1 surface with one boundary component. So this is an example of a genus 1 fact. So in this data graph, there's only one other option of how to orient the vertices. So if I did other orientation, I would actually get the pair of pans, which is not, it has more than one boundary component, so that's not what I would say. Okay, and so what we really want to look at, right, is these continuous maps of a surface with one boundary component, and look at the homotopy class of the image of of the boundary. So basically I want to say that it in a certain sense reduces into looking at continuous maps over a graph. Because if I were just given, okay, so sorry, it's still not showing, but if I can retract my surface with one boundary component onto a trivalent graph. I mean, here it's just the same with like the standard generators, but I separated them so it's trivalent. So really this graph, which is the same as just speaking with. I'm just saying as a surface with one boundary component retract onto a fat graph or a Riemann graph. So essentially what we want to count then is to think about, I take a fat graph, in fact I'm going to take an actual graph soon, but I want to look at ways to map this into here up to homotopy. And there is some annoying stuff that one has to take care of, because you can have a curve gamma in here that appear as a continuous image of, so like in this genus G fillings could be two non-homotopic ones getting mapped to the same one, but generically that does not happen. Okay. So let's talk about counting graphs. So let's fix a trivalent graph. It's just a graph now, not a Riemann graph, not a flat graph. So I'm going to call it a realization of a graph. It's just a continuous map of a graph into the surface such that each edge gets mapped to a geodesic segment, non-trivial. Okay. And G, script G is going to be the set just of all realizations, which I equip with a compact open topology. The length of a realization, so it's just going to be the length of the image, just add up the length of all the edges. And so G, script G of L is going to be the set of all realizations of length bounded by L. Okay, so the components of this set of all realizations just corresponds to 3 homotopy classes of these realizations. And generically, so let me say, suppose each length of each edge gets mapped to geodesic of at least some lower bound length, and let's say that the angles between each one is at least pi/2, like they don't fall back on itself. Then each such component you can straighten it into what we call a critical realization. So it means that at every vertex you make the same angle, so 2pi/3. But it really is a critical point of the length function. That's why I use the word critical. But it really just think about like pulling tight. That's what this is. So if we want to count homotopy classes of these realizations, and each connected component has each connected component corresponds to a homotopy class, and we want to count the homotopy classes. It's the same as saying we want to count the critical ones. So that's what we're going to do.
Sorry,
Yeah.
did you say what you meant by generically?
No, only a hand wave. So I want them to, I guess, that all the edges are long. There's some lower bound, such that the image, the realization maps into something where all the edges are longer than that. But I mean, really what it will mean is like when we can count all of them. Things are going to grow exponentially, so one can ignore things that are not long. And it's the long ones, and you don't want them to map back onto it.
Okay, but the point is that you can actually find examples of things that actually have several critical realizations.
No, so it might have none.
Yeah.
It might, I can map it all to points.
Okay.
Sorry.
Oh, yeah.
Yeah. So it never has more than one.
I see.
Yeah.
Okay.
So it's the uniqueness, I guess. That it exists.
Okay.
All right. So how do we count the critical realization? So let me, instead of the script G, use the normal G for this is actually a discrete set. So G of L is going to fix my graph X. So it's all the realizations on my graph X that are critical, and we want to count those. And we do. So we prove that they grow like this. So I really want to talk about this, just how this relates to counting these things of fixed commutator length. But so we have the exponential e to L, and we have L to a power that depends on the Euler characteristic of the graph. That's what that's supposed to mean. Again, the constant, we can say what it is whatever it is, but it only depends on the Euler characteristic of the graph and on the Euler characteristic of sigma. So it's just a topological constant. Okay. So I claim that this theorem 2 implies the theorem 1, which was the asymptotic of, so the closed geodesics of hyperbolic length to most L of fixed commutator length. That's the main theorem that we're going to prove. And well, theorem 2 is what is here, but we can also see it as a number of homotopy classes of graph realizations. Okay. So I feel like I'm going very quick, so stop me. Too fast. All right. So why is this? So what we do, so we have this, we have fact graphs and we have realizations of actual graphs. So what I want this set to be is, okay, there's should be some dependence on G. So X should be a fact graph of genus G. So remember that's one, so the fact graph is an oriented surface of, with one boundary component and genus G. So X is a genus G fact graph. And but the realization is just of the underlying graph, because that's what we've been talking about. Up to some natural equivalence, so we say that a pair of a fact graph and a realization are equivalent if there exists a homeomorphism between the fact graph structure, so one that actually preserves the structure as well, such that these are not. Okay, it's just not so important. Okay, so I'm going to look at this set, and I'm going to define a map that takes one of these, takes a pair like that, and maps it into the corresponding geodesic. Right? So this, remember that this maps. This is a map from the graph into the surface. Okay. So generically, so again, I'm not defining this, but when things are long enough and nice enough, this is actually an injective map. So this is what I was saying before, that so you could have a curve gamma that appears as a boundary of two non-homotopic things, but generically that doesn't happen. And generically, the image is actually contained in this set that we want to count. Right? So I mean, technically you could have so this could be a genus G, so G is this one that I've got to write here, but there's actually a smaller genus 1 that also maps to it, and then the graph is not, the curve is not, does not have commutator length G, but something smaller, but generically they actually map to it.
Sorry, I'm going to ask again.
Yeah.
Generically here means a proportion.
Yeah.
That's what I should think of.
Yeah.
You can just
Sorry.
don't
Yeah. So okay. So let me say. So generic means that the proportion of all of them. So I guess as L goes to infinity.
That tends to.
That tends to. And so when I say generically here, there's a generic subset in here, and there's a generic subset in here, such that between those is a bijective map. And this is, so there's definitely something to prove here, but this is nothing hard. So I'm just saying that the length of the realization, so that's just the length of the image of a graph, if that's L, then the length of the corresponding curve is about 2L up to an additive constant that just depends on, I guess, the number of vertices of the graph or something. So it's just, so what is my curve? My curve is right the boundary of this thing, so it essentially goes twice over every edge. And that's where it is.
Oh, so the L is the sum of the lengths of the edges?
Yeah.
All right, okay.
Yeah, so the boundary is basically twice.
Yeah.
All right, so putting this together, what I'm saying is that this map, I can actually view it as a map from here to here. So these are these things, but where the realization is as length L over 2, and it maps into, or did I switch the L and L over 2? Which way should it go? So these are the actual curves in my surface, length at most L, that the commutator length G. No, it should be right. this is, yeah, okay. But, and this is what I want to count. So if I can count this, then I'm good. Are you okay with it?
No, we're just thinking about we're behind you, so we're thinking about the additive error thing.
Yeah.
Anyways, what maybe we
Yeah,
can-
I thought, yeah. But it's basically, this hyperbolic geometry is just how far is,
Yeah,
what's it?
but
Yeah.
the edges, so your graph are coming out, you have these 2 pi over 3 angles.
Yeah.
Right? And so this, you're saying that this doesn't, so you get an additive error when you go to
Every time you pass.
every time you
origins.
pass through,
Yeah.
but then how does that disappear then asymptotically?
No, so okay, no, yeah, so I mean, I really should write this as like, I guess it's minus a constant or something here.
But there should be okay.
But then everything goes like e to l something, so e to l plus a constant is a constant. And it comes like, yeah. We can
How
have
does
it.
e to the L plus the constant, right?
Well, that's e to l times e to the constant.
Exactly, yeah.
Yeah. Yeah, so there's a constant that comes out. But,
Okay.
yeah. But the asymptotic, yeah.
Okay.
Alright, so all I'm saying is that the cardinality of this is approximately the cardinality of this. And now one can say what the so this is not what we counted before. What we counted was these actual realizations of an actual graph, not a fat graph. But one can relate the cardinality of this with those by, so here I'm summing over every fat graph that has genus G. So x overall, x that are genus G, and the number of realizations of such a graph. And then I just have to divide out by the automorphism. These are preserving the fat structure. Right. So this is what we proved before. I mean, that was the theorem 2. And this number, luckily somebody else had proved. So that's where we have all these factorials and exponential. They're not constant. It comes from this. Bacco, Godovina. Sorry if I'm mispronouncing them. Okay. So that's exactly this thing here. I mean, they stated it about this one vertex triangulations or something, but it's so from that, just putting it together, you get what. So that was that theorem, and this is the concept. Okay. So if we can count these critical realizations, then we can also count this thing that we wanted to count. So let me say a few words about how one can count graphs. Right? So we fixed a trivalent graph, and script G was just a set of all such realizations with a convex open topology. But in fact, we can view this as a hyperbolic manifold itself, because we can take any realization and map it to the tuples of vertices. Where does it send each vertex on my graph? So that's it. So this is supposed to be as many copies of our surface as we have vertices in the graph. The graph is fixed. And this is actually a cover map. It's a covering. So every realization has a neighborhood. So if I take a realization and look at it, its neighborhood, it's parameterized exactly by where it sends the vertices. Because any arc between two vertices, there's a unique geodesic between them. So this can seem to be a covering map. And so we can pull back the product hyperbolic measure. So this is hyperbolic manifold locally, so it's locally modeled on B copies of H of the hyperbolic. Okay, so I'm going to do this because I'm going to want to compute certain volumes. So now I'm going to do, so I'm not going to look at those that are exactly critical, so they're not exactly 2 pi over 3 at every vertex, but I'm going to thicken a bit to have an epsilon error. So up to plus minus epsilon, the angles are what we want. And then I'm going to look at the subset of the realization that are so-called epsilon critical. And then, so remember that we said that each connected component of G or component of these contains a unique critical realization. So let this denote the component that contains. Yeah?
Can you just say again, what do you mean by hyperbolic manifold there?
So this is a covering map. So I'm just pulling back the. So I think each connected component, each of these connected components is just going to be a product of hyperbolic lengths.
It's a product.
Yeah.
Okay.
Yeah.
Okay. It's a product.
Yeah, sorry. Okay, so it's a manifold with, okay. Yeah. Yeah, it's a product.
Okay.
Sorry. Yeah. Alright, let me see if I, yeah, okay. So now, I guess we noted this before too, but so the number of components of this thing is the same as the number of critical realizations. So we want to find how many components this thing. Alright, so let me just, I'm going to show an example where these things make more sense, but let me just say it more general. So this is just, remember that this, by definition, was a sort of a non-strict of a normal G, is just a critical realizations, and we just said that's the same as the number of components. Now it turns out that one can compute the volume of this set, so all the epsilon critical realizations. And just this boils down to basically counting lattice points in hyperbolic space. So those are its lattice point counting. And one can also compute the volume of each connected component, and it turns out that they're all the same, asymptotically this, just using basic hyperbolic geometry. And therefore, what we need is just a ratio of those two things. So let me come into why one can compute these things, but in a slightly easier setting. Namely, let's take X to be a loop. So before X was always a trivalent thing, but let me do it for a loop where it's much easier, but actually the same techniques work in the general case. So if our graph is just a loop, so I mean it just has one vertex and one edge, then the set of realizations are maps from the loop into our surface, such that the edge is geodesic. So it's just geodesic loops. So I'm going to call it L instead of G, just so you remember, it's just loops. All loops. And what I mean for it to be critical, well, I want to pull tight, so it's when this meets at angle pi, so it's a closed geodesic. So that's what I called C before, so we know it's C. So in this case, what we want to count, so we want to count critical realizations, we just want to count closed geodesics. It's Hoover's theorem. So we're doing this, what we've been doing is just Hoover's theorem. So we have this cover now from L into this maps each realization to vertex with vertex, and now it's a hyperbolic surface. Okay. I think it's actually cylinder. I mean, H mod set. Okay. So, and what we want, so what we were saying is that, so G has become C, that the number of closed geodesics with length the most L is the difference between, so the volume of the set of all epsilon critical ones. So again, that's just when instead of pi, there's an epsilon error. And this is the connected component containing a critical one, namely a geodesic. So I need to compute these two and take the ratio, and hopefully we get E to L over L, because that's what Hoover proved, or it should be. So how can we compute the volume of all the epsilon critical ones? So let's first fix a point in our surface and consider those loops based at that point, and then I'm going to vary the point. So first, this is the lattice point counting I was saying. So Delsart proved in the 40s, so it's very classical, that the lattice points under a Fuchsian group hyperbolic plane equidistribute. Meaning if I fix any point, so here, so gamma is going to be the Fuchsian group that we put up right to get our hyperbolic surface. And I fix any point, and I look at, so this is my point, the blue one, and I look at this orbit under gamma, that's all the red ones. And I look how many are there in a ball of radius L. So they equidistribute, meaning that it's proportional to the volume of the ball. So it's the volume of the ball divided by the volume of the surface. And my hyperbolic geometry, the volume of the ball is asymptotic to pi d to L. So we have this. But then, basically using the exact same arguments, this follows by the mixing of a geodesic flow. One can show that, I mean, this is also well known, but, before I say that, let me say, notice that this is the same as saying how many loops are there based at a point on my surface. So x is the projection x tilde. So I'm just replacing, take a geodesic line from those. So number of loops, so not anything about them being epsilon critical, just loops based at a point of length at most L row lengths. But one can actually also, so that's what I was trying to say, that the directions equidistribute. So this picture is tiny, it's going to be, you can't even see what it says. But if I look at, so on my surface, how many loops are there that enter this in some segments? So some, I think there's a delta part of the entire 2 pi. There's delta over 2 pi of them that do that. So like these also equidistribute. So more generally, if I take any open set, so I fix my point on my surface that I want to enter, and so what I want to do, I want to exit it at a certain angle and enter it at a certain other angle. So how many loops are there based at a point with the initial direction and terminal direction inside this open set? Well, that's proportional to the volume of that set. So the volume of U divided by the volume of this, so volume of U over 4 pi squared times the total number. So again, just equidistribution of this thing. And what we're looking for when we look at epsilon critical, well, you start your loop however you want, 2 pi, but once you've chosen how you want to exit it, then you have to come back in a 2 epsilon area here, so that it meets like we want. So what we get is that the epsilon critical loops based at x is asymptotic to so 4 pi epsilon over 4 pi squared times this. So cancel epsilon times e to L over the volume. Right? So what we want to compute is this, but what we computed is those epsilon critical loops that are based at one point. So we vary the point integrated over surface, we get epsilon e to L. Okay. So this is the volume of this, and now we want the volume of each connected component of this, and then divide it. Okay. So sorry, I'm almost done. So let's look at this. So I take a component that contains the critical, so the geodesic gamma. If I just take the cover corresponding to gamma, let's suppose it's primitive. It works if it's not true. Also if it's not primitive. So as a cover corresponding to that, I can look at the map that sends. So I take any point in here. I take the unique loop, geodesic loop based at that point. That's freely homotopic to the geodesic. So I have this map. Then isometry, I guess here I'm calling x both the point here and x on the surface. I guess technically it should compose with a projection to the surface. Then the volume of all such things, right? So the higher up x goes, the bigger the angle defect is going to be. So I take the worst case, the epsilon over 2. There's also a symmetric picture down here. So I need a volume of this. So I take its, so the 2 is from, this is the volume of this segment here. So it's t times the length of this. So it's this. So we have to compute d. How does one find d? One goes to Peter's book, and in the end of the book, there's formulas that tells us how to compute d, and it's this. Sorry, that picture shouldn't have been there. So so this formula. So when epsilon is very small and L is very long, so this is approximately 1, and this is approximately epsilon over 2. So d is this. So just computing it, we get that volume is epsilon times L. So putting it together, we have computed these two, and together you get each one. And then so the same kind of arguments works for trivial, you just have to some more bookkeeping, but otherwise it's.
Any more questions? Or comments?
Well, they were counting
Like one vertex triangulation.
one vertex
Yeah.
triangulation. And
Yeah.
how does that, so you're basically, that's the same thing as, like, if you look at the dual, that's going to be the same thing as your
Yeah.
ribbon graphs. Is that right? Yeah. Okay. And can you, does that mean asking for two vertex triangulations makes sense? Or, is there a version of that for your problem?
For what problem?
Well, instead of looking at, so you wanted to always think with one boundary.
Yeah.
Does it make sense to look at things with two
Oh, I see.
boundaries?
Yeah, I don't know. So actually so the first version of this paper was only counting immersed surfaces, which I never came back to. And then actually we could have done it with many boundaries.
Okay.
But then we started doing this with commutator length, and then it didn't make sense anymore. So we can yeah. So at least when it comes to immersed, we can count.
But you need an equivalent formula for the number of triangulations with.
Yeah, I agree. Okay.
You take that as a product.
Yeah.
Consequence of it. Whatever that number is.
Yeah, exactly. Exactly. Yeah. Okay. Yeah, so we might not have an actual constant for that.
Okay.
More questions? So, this So, the next speaker is Viveka Erlandsson. He's going to talk about there is no veil. So worthy of geodesics for all.
Changing
Without the
Here's where orthodox.
okay.
Thank you very much. And thank you. What? Thanks to Gabino and Ernesto for organizing this. It's really nice. It's really nice to see a bunch of old friends and meet new people, and it's great to be here. And what I'm going to talk about is stuff that some of you might have heard before, at least part of it. But because I haven't seen some of you in a while, I thought this would be a good excuse to talk to you about some of these things. And also because I'm still thinking about them, and there's some new stuff which I will never get to, but anyways, this is why I chose to talk about this. So, I tried to make this is not coming out very well, actually. I'm wondering if there might be a better way, whether we could attach this to my iPad. Can we try just to see if it visualizes better if we attach it directly to the iPad?
We can try.
Okay, well, let's just leave it like this and then we'll see what happens. Okay, in any case, I thought because the audience is somewhat mixed that I would take a step back and talk about sort of an elementary example. I might have taken this too far in terms of how elementary can you possibly get. So I want to tell you about a nice theorem that's called Viviani's theorem. Viviani was actually an assistant to Galileo. And recently, this is completely different. I listened to a podcast about Galileo, a podcast that spends its entire time explaining why Galileo was among the world's largest idiots. And it's very impressive. Anyways, so this explains why Galileo apparently wasn't very good at math, and this is why he had math assistants who were presumably good at math. And this is one of Galileo's assistants, Viviani, and he proved a nice theorem. And so it starts off with just your usual equilateral triangle, and this is what you do. You take a point on that equilateral triangle, any point on the equilateral triangle, and you look at the three orthogonals that you get that reach the boundary of the triangle. Right? You call them H1, H2, and H3. Right? And Viviani's theorem is that when you sum this, this is equal to a constant. Right? So you can say, well, that's true for anything. But the point is that if you change the point P, the constant is still the same. So that's the point of the theorem. So you get it. This is always the same constant. And as soon as I show you the proof, or maybe you've already figured it out, then you'll see what that constant actually is. So here's the proof. There's the picture. The proof is you take that point P and you look at the lines to the vertices. Okay, and this gives you three triangles. Right? You color with different colors. And well, the sum of the three areas that you get is equal to the area of the whole triangle. And so that's the proof, right? Because the area of each triangle is 1/2. If you take your equilateral triangle has side length 1, and the area of each triangle is 1/2 times the height, and then you have this formula here, and by a very complicated formula, you can figure out what the area of an equilateral triangle is of side length 1, which happens to be √3/4. So this is how you get this Viviani's identity, right? Anyway, so that's what I wanted to talk about. Thank you very much. So there you go. So that's. I just want to make a few remarks about this. First of all, this sum is constant. If you have a Euclidean triangle, it's constant if and only if the triangle is equilateral. Right? So if you take a non-equilateral triangle, this sum is not constant. Right? That's not so difficult to see, but I think somebody proved it in the 70s or something like that. So that sort of appeared in Euclid. So that's kind of an interesting remark. And then you can generalize this in many different ways. Okay, there's many different ways you can generalize it. You can look at parallelograms, you can look in higher dimensions, you can do all sorts of generalizations. Okay? This is a very nice. But one thing you could do, because of the audience here, and because we care about hyperbolic geometry, is well, why don't we look at hyperbolic triangles? And here's everyone's favorite triangle, right? Because, well, frankly, it's ideal. So here's everyone's favorite triangle is right there. And so we look at this one, and you can do the same thing. So you can just take a point, any point in the triangle, and you look at the shortest paths to the boundaries. And these are the first instance of something we'll see more generally, which are orthogeodesics. Alright, and so you look at these three paths, and then you ask sort of a similar question. So what you can do is, alright, so we can do exactly the same thing I did as before. You look at the lines that go to the vertices, which are at infinity. You break it up into three triangles, and you can compute the area of the triangles. And once you've computed the area of the triangles, then you're going to get an identity just by saying that the sums of the areas of the triangles is equal to pi, because pi is the area of the full triangle. And so here, I mean, as Viveka pointed out, there's a page in Peter's book which you can go to figure out that so how do I get the right determinant? Oh, there. Okay. So this formula here, when you have that gives you actually a formula for the area of that triangle, so the angle theta I is exactly that angle that's there. And that's what the area of the triangle is. And so in fact, another reformulation of this identity is just to say that the sums of these three angles is equal to 2 pi. That's another way of thinking of it. It's the same identity, just reformulated in a different way. Okay, and if you write this down, you get an identity that looks like this. So the sum of the arc sines of these angles, which turn out to be expressed as hyperbolic cosines of the heights, is equal to pi. All right, so this is an identity. And this is sort of a prototypical identity for the type of thing that I want to talk about. Okay, and again, of course, observe that the feature of this is that if I move the point P around, the terms hi, they change, they vary. The terms, of course, the heights vary, but the formula, the sum of these functions of hi does not. Okay. So, what about less ideal triangle? Okay, I'm just trying to see why it's coming out. So, anyways, so what about less ideal triangles? So you can look at any hyperbolic triangle and ask the same question, and you look at the sum of the heights, and in fact, you get inequality. This is sort of similar to what happens for Viviani's theorem. You get equality if and only if it's constant if and only if the triangle is equilateral. Here you get equality if and only if the triangle is ideal. And you have this sum. So it's a characterization of ideal triangles among all triangles. And so, because it's the only one for which it's equal, now we know why it's really ideal. This is the... All right, and here's something else you can do. Oh, wow. You can't see anything here. All right, this is actually that's weird. Why is because this means that we won't be able to see any of the curves that I drew. So you can't, let me see. Let me just try something very quickly. This is not a good idea. So we have I have an...
Yeah, then we have a universal thing.
Do you have a universal thing that goes to HDMI?
Some.
Hold on. I think I have an adapter. Hold on, I'm going to try something really quickly.
Should I remove this?
Sorry?
I remove this.
Yeah, try that, and then I'm going to try to put it on here. And then, here you have this one. So we have this one to this one. This is never going to work. And then we go to here. And then, hold on, what happens here? Is anything going to appear?
No, just looking at the wall. Yes. I think we'll have to try.
It's just like that. It doesn't seem to be. Oh well. Okay, but I don't know. So what are you reading the PDF with? Do you have something else that could read the PDF? Because only half of the picture is appearing. You can open it with something else?
Oh, sorry, yes, this was...
Okay, well maybe never.
But this, is this... What is this exactly?
It's the Adobe Pro. I don't know why only half the pictures appearing.
One second. Let's try something.
Okay. Yeah, it does the same thing.
That's the same.
It's very good. Okay, well listen, we'll go back to it and then I'll just describe it. It'll be a descriptive aspect.
Can you copy maybe another copy?
Sorry?
You want to take a copy of this?
No, never. Listen, I'll just go forth. Sorry. So let me just put this back how it was. Do you remember how to reconnect this?
Hopefully, yeah.
Okay. Okay. Like that. All right. So sorry for that interruption. So here's something else you can do. So if you look at a hyperbolic torus, this is a hyperbolic torus with a puncture. You can do the following thing. Okay, you can look at curves that we can't see here anymore, but that were there originally. So you look at simple closed curves on this, and you look at all simple closed curves on this, and you look at their geodesic realizations. And you get the following formula, which is due to McShane, which is that the sum of all these functions, when you look at sum, you're summing over, oh, I did something funny there. I'm summing over alpha, but I wrote gamma. Okay. So that's supposed to be the sum over alpha, which is of length of alpha. And you sum over all the lengths of simple closed curves, and you always get 1/2. All right? So this is the famous McShane identity. And again, what's remarkable about this is the following thing. So you sum over all the simple closed geodesics, and so the way you should be thinking about this is you have a moduli space of all possible once-punctured tori, okay? And each time you take a point that lies in that moduli space and a homotopy class of closed curve, you get a geodesic realization. So this gives you a function that associates to an element of your moduli space the length of the geodesic that corresponds to that free homotopy class. So this is exactly as Viveka was talking about before, as Gu was talking about before as well. All of these lengths, these are functions that vary over your moduli space or your Teichler space. And with this length function, the way you should think of this is that the sum of the lengths is equal to 1/2, where the length, of course, depends on your choice of hyperbolic structure. As you move that hyperbolic structure around, the individual terms, the individual summons that are here vary, but their total sum does not. So that's one of the interesting aspects of the McShane identity. Okay, so something different. So in my title I had the word orthogeodesic. So what is an orthogeodesic? It's a geodesic path, okay, that's embedded on the surface, and that's orthogonal to the boundary in both of its endpoints. Right, so here are two examples of orthogeodesics on the surface. Right? And sorry?
You said embedded, like that immersed.
Oh, sorry, immersed. Yeah, sorry. Locally embedded. Right. So geodesic arcs on the surface, right, that are orthogonal, twice orthogonal to the boundary. And here's another identity who's due to Ara, that's here in the room, who can tell you more about it, which says that you take these lengths, you get a function, a natural function of them, which is the log of the coth to the power 4 divided by the length divided by 2. Okay? And you sum these up over all possible orthogeodesics that you have on the surface. Okay? And what you get in the end is the boundary length of the surface. So for this identity to make sense, you need to have geodesic boundary. You need to have a surface which actually has geodesic boundary. Right? So this is a I mean, what's interesting here, as opposed to the McShane identity, something to point out, is that what you're getting out of this sum is actually a geometric, an important geometric invariant associated to the surface. Right? So you're actually computing something that you didn't know before. Right? Before Greg McShane proved his identity, everybody knew what a half was. Right? So that wasn't new. Right? The half wasn't the new part here. Right? But if you're given a hyperbolic surface, it's not obvious what the boundary length is, right? So this is something that you're actually getting out of this identity. And so again, I sort of want to look at these two identities. And this is how this whole project occurred, is that I've been looking at these identities for years, fascinated by both of them, and of course wondering in which way, or if these two identities are related, okay, in any way. So you look at this identity here, and you're summing over you're summing over all orthogeodesics. And I'm going to explain more about this in just a second, but when you look at the McShane identity, you're really summing over simple orthogeodesics. Okay? And in the general form, so if you have a surface here that has a cusp that goes out here, the cusp is so the cusp is somewhere there, but all right, so in this identity here, when you're no longer in a torus, the identity becomes slightly more complicated. So what you look at this time is embedded pairs of pants, not immersed, but embedded pairs of pants. Okay? And you look at the two boundary curves of this embedded pair of pants, and you sum over them, and you always get something equal. In this case, it's equal to 1. Oh, that's actually wrong. That should be half. Okay, so that should be a half. All right. Whoops. Anyways, okay, this should be a half. Okay, but it's because of the projector. It's not the 2 is not showing up. Like the curve before, this is the 2, and it changes alphas into gammas too. This is really a terrible setup. It's really bad. Okay. And so the goal is to sort of interpolate between these two geodesics, and there's pictures here that you can't see, but they're really nice pictures that I but you can't see them. But anyways, it's really nice. Yeah, I can see them here on the screen. If only you could see them. Nice square. Nice square. Anyways, and so basically the question that I'm really interested in is our best major and McShane actually related, which is a very deep question. Okay. All right, so I just want to make one observation before I go on, and that is that if you look at the index set in the McShane identity, so you're looking at these embedded pairs of pants, and associated to an embedded pair of pants, you can associate a unique simple arc. And in the same way, you can think of this as a unique simple orthogeodesic. Okay, and so these are the 3 representations of the same topological object. Right? Here we're thinking of just a topological surface where the boundary is represented just by a marked point. Okay, and we look at an arc that goes there, a simple arc, and associated to that we sort of have, we do have an embedded pair of pants, and we have a simple arc, and it has boundary curves. Here we have a simple orthogeodesic, right, and a pair of pants, and here we have also a simple orthogeodesic and a pair of pants. And so these are always in one-to-one correspondence, simple arcs, right, embedded pairs of pants. These are the same objects. And so in particular, what that means is that when you look at the Bass-Magen identity, you're looking over a sum over all orthogeodesics. And when you look at the McShane identity, you're looking at a sum over simple orthogeodesics. Right? So this was the starting point, sort of as an observation, is that you have a containment of the index sets. So when you look at the Bass-Magen identity, you're looking at many more orthogeodesics than if you look at the McShane identity. And as Viveka was explaining earlier, there's all these counting problems. And in fact, if you look at sort of the size of the index set as it increases with length, and Peter was talking about this too, of course, that if you look at simple orthogeodesics, I mean, nobody actually said exactly this, but it's all true, the number of simple orthogeodesics grows as a polynomial of L, whereas the number of all orthogeodesics grows exponentially. So you're looking at you're looking at a very sparse subset of the set of all orthogeodesics. But nonetheless, there's this relationship between them, and you sort of want to know what's going on. Okay. So the other thing I want to point out is that when you change so I mentioned one instance of the McShane identity when you had a cusp, but you can actually also find a McShane type identity if you have either a geodesic boundary, or if you have a cone point, and these different generalizations are due to different people, namely to Merzacani, to Tan, Wang, and Zhang, for the case of boundary and cone points. Okay. And then if you look at the Bass-Magen identity, well, you try to bring it to a cusp, and if you just do this in the obvious way, this identity disappears. Right? So both the length on the left, you have the length of the boundary. Well, if you go to a cusp, the length becomes 0. And each of the summons also goes to 0. So you have a very interesting identity, which is 0 is equal to a sum of zeros. But there's not much to be said. But you can still make sense of that, and that's joint work that we did together with Ara and Serpio 10 to actually make sense of a way to get to to get to a cusp, to be able to understand that in a meaningful way, and that requires changing the index set, grouping things together so that they don't disappear. You know, together people are stronger than by themselves and all of that stuff. And so it's a group effort. Okay. All right, so what I want to talk to you about today is something that is another way of thinking of this. And for this, it's really a topological discussion about arcs and curves on surfaces. The only thing I want to insist on today. Right? And it's the following thing. And so I look at the set of all curves on the surface. So this is curves up to free homotopy. I'm looking at them for technical reasons, and well, not even technical reasons. I'm thinking of them as oriented objects. I'm not getting rid of orientation. And in the same way, I'm looking at arcs that have endpoints in my set of fixed points, and I'm thinking of them again as oriented, and up to free homotopy that fixes the endpoints. Right? So these are the two objects I'm interested in: curves and arcs. Right? And I want to put relationships between curves. And here's a structural type of relationship that you can have between curves, is that you can say that one curve supports another if the first curve contains the other as a proper subloop. And so here's an example that luckily for us is that the computers decided not to erase completely. Right? So you have this curve alpha which goes around, and in the process of that curve alpha, I have sort of this subloop that goes here and goes around, right? And because this curve alpha has self-intersection points, there are non-trivial subloops that are formed as subloops inside that curve alpha, right? And so in this case, we say that alpha supports beta, right? So that's just a definition. Right? But this gives you a relationship between two curves. Okay? And so we write that beta in some sense injects into alpha. Right? So that's just a definition. And you can do the same thing with arcs. Right? You give yourself an arc, and this is an arc that leaves from an endpoint and goes around, and you say that the arc supports this curve if that curve is a subloop of that arc. Right? So this is just a definition. All right. Okay. And here's the main concept that's going to go into this. It's the idea of coherent marking. So what it is a subset of all curves, okay, that have the property that if you have a curve in this subset and you take another curve in this subset, then one cannot be supported by the other. Right? So this is like the opposite of a help group, right? Nobody's allowed to support anybody. Right? So you're not allowed. It's a very There's no support provided by anybody in this group. So you're coherent if nobody supports anybody else. Okay? So it's a group of individuals, right? So if for instance, if we had this curve alpha, and I look at that subloop there, well, that subloop cannot belong to my coherent set if alpha already belong to that set. Right? So once you have a curve, all of its proper subloops that you see inside are not allowed to belong to that set. And that's what I say by a coherent set of curves. Right? So let me give you some examples. So here's an example, the empty set. Right? So everybody's unsupported with the empty set, so that's fine. Okay? So that works. Here's another example, is you just choose any curve. And keep in mind that this curve is an oriented curve. So you can choose a curve with one orientation. That is a coherent set. Right? Or you can choose, for instance, all simple curves. Right? So simple curves form a coherent set. Because simple curves don't have any other proper subloops. Right? So they can't support anybody. So simple curves are all individualists. Or if you have any coherent marking, you take any subset of that. Right? So if you had a coherent set, then you just take any subset of that and that gives you a coherent set. Right? So these are all examples of coherent subsets. So the theorem is that if you have a coherent marking, you get an identity. Alright? So that's the thing, right? And so we're going to unpack this a little bit, but that's the basic idea. Okay? So what is this? What are these different elements in this theorem? So the first thing is, so we have this coherent marking, and what this O of M is here, which you see here in the subset. So this is the set of all the orthogeodesics, or arcs, in this it's topological notion, right? All the arcs that are unsupportive of any element in my coherent set, right? So these are the forbidden groups. So those are those. And then here you have the second set that I have. Yeah.
So the marking only contains closed curves, not arcs?
Yes, it contains closed curves. The marking is on the set of closed curves. Exactly. It's a subset of the set of closed curves. But arcs can be supportive, can support closed curves, whereas curves don't have that luxury to say they are arcs. And the ones that I've written O of alpha of M, those are ones that are peripheral to alpha. So that's sort of so they don't support alpha, but they're peripheral to alpha. So here's an example, right? And luckily it also appeared. So you have an orthogeodesic or an arc that leaves from the boundary and comes back like that, okay? Right? And I can add to that just that little bit there, right? And I could add that on one side, I could have added that on the other side. Right? But I added that on one side, and that gives me a homotopy class of closed curve. And that means that eta is peripheral to alpha. That's what peripheral is. Right? So an example is, I have a point, and I take a simple arc. Okay, it's peripheral, and now I let that. There's two possible homotopy classes of simple curves that I can think of. The one that goes on this side and the one that goes on that side. I'll come back to this example in a second. And in that case, that arc is peripheral to both of those curves. And so the point is that what you have here is a sum. And this is a function that I'll tell you more about in just a second. And here's a function. And you sum over all of these things. And what you get in the end is the length of the boundary. So let me just say a little bit more about the index sets. So first of all, if you take your coherent marking to be the set of all simple closed curves, then every non-simple orthogeodesic is supportive. Right? So what does that mean? That it's simply the fact that if you take a non-simple arc, it necessarily forms a simple loop somewhere. And so this is like a closed curve on the surface. There's always a simple loop that's formed by a closed curve on the surface. Right? This is an observation that Peter taught me many years ago. Right? This is a nice thing. And so, for example, in this picture here are two simple loops that are formed by this non-simple arc. Okay? It works for arcs as well. Right? So that means that, in particular, that if I've chosen my coherent set to be all simple curves, then every single non-simple orthogeodesic has to be supportive. So in particular, the only ones that are going to be unsupportive are the simple ones. Right? So only the simple ones can be unsupportive. So what that means is that so now I look at a simple orthogeodesic, and I'm saying that it's peripheral to two simple curves. So what are those simple curves? They're the simple curves that I get just by adding in that bit, and then I get a curve there, or adding the other bit, and then I get that curve. So it's peripheral to both simple curves. I mean, I shouldn't be saying all of this with orientation, but this is also true. Okay, so in fact, what this tells you is that the identity, if I used the coherent set, this actually results in exactly the chain. This is exactly what it is. So if I set my coherent set to be all simple closed curves, then the identity that I presented before is exactly the chain. Right? And now, if I look at this identity again, and this time I take as a coherent set the empty set, well then what happens? So all the unsupportive orthogeodesics become all orthogeodesics, Right? So I get all of them. Okay? And if you look at this term, well, this term is going to disappear because I'm taking a sum over the empty set. So this whole side disappears, and the sum here is over all orthogeodesic, and this really becomes the Basmagian identity. Okay. So, just to point this out again, is that the set of this, no matter what your coherent marking is, it always contains the simple arcs. The set of unsupportive, saying that another way, the set of unsupportive orthogeodesics always contains the simple ones. Right? So that's the point. And then you have this world that sort of goes between the McShane identity, which is in some sense one extreme of this, and the other extreme is the Basmagian identity, and then you have all possible coherent markings in between, and there's uncountably many of them. And so this is what I wanted to point out. And so, for example, here's another example of a coherent set that's kind of interesting, at least to me, is that you can, because this is one of the other original things that I was thinking about. I kept getting the question: is there a McShane identity for curves with 18 self-intersections, for instance? Well, there is. And this is exactly it. So then you take as a coherent set the set of all those curves that self-intersect 17 times. Well, then you get an identity by adding this as your coherent set. All right, so let me just finish with some explicit formulations of this. So here's an explicit formulation of this. So this is just a surface with a single cusp. And here's what the formula actually looks like once you actually write down the formulas of the notation. All right, and so you get something that looks somewhat similar to the McShane identity. So you have a 2, which may or may not be correct depending on the thing, but I don't know. Okay, and so what you sum over here is you sum on this side. You have a sum where you're summing over alpha. Okay, whatever your coherent marking is, whatever it is. You take exponential minus the length of the 2. And here you sum over those that are peripheral. And here you have to be a little bit careful because the orthogeodesics, in the case when you have a cusp, the orthogeodesics, their actual length is infinite. So what we're doing is we're cutting the orthogeodesics off a horocyclic neighborhood. Right? And we're looking at the restriction of that. So that gives you a finite length. Right? So you move from here and then you go around. Possibly you go back into the horocyclic neighborhood and you come back, but you have to be orthogonal twice to the boundary of that. So that's one explicit formulation. So here's another explicit formulation. If your surface actually has boundary length, and you can write down these functions, this is what they look like. So in the first set, you get the Basmagian term, which is exactly the same as the term I wrote down for the first thing, except for what? What's the difference? There's a 2, right? Right. Because my arcs are oriented.
You had a 2 in the beginning, too.
No, I had a 4 for yours.
Oh, I couldn't read it.
It was the projector. And so here you have a Basmagian term, and then here you have something that, so this term doesn't really look like this doesn't look like the McShane term that you saw with the surface with the cusp, but this does look like the McShane terms that you get if you look at the Mirzakhani or the Tan-Wang-Zhang formulas. This is similar. It's not exactly the same term. There's a reason for that. There's a geometric reason for that, which I'll explain very briefly, which is the following thing. Oh, well, we can't see that at all. Okay, well that's good. But I just want to say with the geometry of what these are, these terms correspond to geometric quantities that correspond to gaps. What you're doing is you're breaking up the boundary length, you're breaking up the length of the boundary curves into small gaps. And you don't see this, but this, in some sense, this drawing here is actually a drawing of the Basmagian gap, but only on one side of the orthogeodesic. And then you go to the end of the Basmagian gap, and then you look at all the things that go all the way until those that spiral around this curve. And that's the second gap that's just there, in between those two gaps. And that's what geometrically those terms are. Anyway, I'll stop here. Thank you very much.
Thank you. So any question?
Yeah.
Realized identity.
Yeah.
The thoughts were also for hyperbolic triangles, not the ideal ones. Hyperbolic equivalent.
No, not. I mean, well, not this. Not the same way. No. It's not constant. If you,
No, it might have on the triangle, but
Yeah, maybe you can write something down, but that one. But I mean, the point is that it's not. I mean, my point is that the sum of the height certainly isn't constant, and I don't know if there's a natural function that is. That's a good question. Yeah.
Can you say a little more about the gap measure? Because, look, in the last formula you wrote down,
Yeah.
right, so that last term, that gap measure is coming from McShane's identity.
Well, it's not. It's,
Yeah, so what's it off by?
So this is actually a measure of the following thing. So if you to measure this, what you do is you look at a pair of pants. You look at the Basmagian gap, right? And you look at the McShane gap, and you retract the Basmagian gap from the McShane gap. But you only look at this on one side.
So you take it away.
You take it away. And what's remarkable is that this only now depends on your left-hand curve and the orthogeodesic. So, in general, just as a philosophical statement, when you look at the McShane identity, you have a whole pair of pants, and just because the pair of pants is determined by the three boundary lengths, you know that whatever you're measuring is going to depend on the three boundary lengths. Right? Just as a general statement. But and then independently of what that function is, there's going to be a function of the three boundary lengths. But what this is saying is slightly different. What this is saying is you can actually split the McShane gap. Part of this that goes into this is splitting the McShane gap into three different parts. One that only depends on the orthogeodesic length, which is your gap. One that depends on the orthogeodesic gap and the right-hand curve. And one that depends on the orthogeodesic gap and the left-hand curve. So you have to be able to split those things to be able to make this work.
Questions? So let's start with So now my program says it's coffee break. I'm not sure. I haven't heard the Italian people.